So when we're dealing with sampling distributions, it's just really important to understand what it is we're discussing. And so that's what I'm going to probably focus on most, is making sure that we understand what a sampling distribution is. So the idea of a sampling distribution is a distribution of samples. I know that sounds redundant, like, okay, it's kind of in the name, but specifically, it will be a collection of sample statistics. So what we will do primarily in this course is we're going to focus on means and proportions, okay? So means and probabilities, so to speak. And those are called our unbiased estimators, and we use those to estimate those sample statistics to estimate the population. Okay, what a sampling distribution is it's a collection of all possible samples with the same size from the population. That's kind of hard to generate, so I'm going to go ahead and do a couple of them, but here's the idea. If we took all the population of all the students at Porterville, right? And I said, okay, so we're dealing with all of those students, and we're going to take a bunch of different samples from them, a bunch of different means, all the same sample size. So I'm going to sample 10 students, and then I'm going to sample another 10 students, and I'm going to sample another 10 students. And for each 10 students, I collect their means, okay? If I take those means and I make a distribution of those means, that is called a sampling distribution. Okay, all those means go together to form this sampling distribution. I'm going to start on a small scale. So what if our population was just three numbers, three people, 4, 5, and 9? Okay, I could go to my calculator and go, okay, 4, 5, and 9, I could figure out the mean of those. This is a population 4 plus 5 plus 9, so that is 18. 18 divided by 3. This population has a mean of 6, right? And the standard deviation, each of those numbers minus that mean squared, added up, and divided by, well, n minus 1, or in this situation be n, because it's a population size, and we'd square root that, okay? And that's going to give us the standard deviation. We could do all that running one bar stats, okay? But what I want to see is, what if I said, how many different ways could I sample just two of the people, two of the three people, right? Well, I could sample the 4 and the 5. I could sample the 4 and the 9. I could sample the 5 and the 9. And I think everyone's been chosen. So these would represent all of our samples with the size n of 2. Okay? Is this a sampling distribution? Not yet. A sampling distribution needs to be a collection of the statistics, specifically either the means or the proportions. Okay? So I'm dealing with means primarily because that's where we're going to start. So if I do the means, these are not a collection of means. These are still individuals. What I would have to do is I'd have to make a collection of the means. Okay? So I'd have to do 4 plus 5 divided by 2. This would represent 4.5. That would be our first mean. 4 plus 9, 13 divided by 2 would be 6.5. That would represent our second mean. 5 plus 9 is 14 divided by 2, 7. That would be our third mean. This right here represents a sampling distribution. It is a distribution of all the samples of the same size for that population. So the question is, how does this sampling distribution compare to the population? Okay, so I'm going to go back here and add a screen first. So here's our population. It was the numbers 4, 5, and 9. Okay, I could do one variable statistics on that population. And if I scroll up, that's where I got the mean of 6 and the standard deviation of, I think it should be 2.16 if I've done this right. Make sure I do this right. Actually, I think it should be the 2.16 since we're dealing with the population. Okay? Well, here's my sampling distribution, 4.5, 6.5, and 7. Four 4.5, 6.5, and 7. Okay? What if I were to find the mean of these means? These represent, right, this was our regular data. This is a collection of means. What if I found statistics on our sampling distribution? Well, notice the mean of our means is equal to the true mean. These two are equivalent. Okay? So for a sampling distribution, the mean of our means equals the true mean. The mean of the means equals or is equal to the true population mean. What about the standard deviations? Were they the same? Well, 2.146, and this one was 1.322. They're not the same, are they? So what we see is that the actual sampling distribution, so this is the first thing we see is about the means, and second, we see that the standard deviation of the sampling distribution is not the same, it's actually smaller. How is it smaller specifically? We're going to get into that kind of near the end. But so far, what we want to see is that we would call the mean an unbiased estimator, because if I do a sampling distribution of means, it estimates the true mean. So the homework's going to have you do a lot of practice where you're going to be finding standard deviations, and you're going to be comparing the standard deviations to the true standard deviation. They will not equal the true statement. So we call those biased estimators. The standard deviation is biased. Ranges are biased. If I find the range of a sampling distribution doesn't equal the truth. The median of, right, if I take a bunch of medians, those won't equal the median of the truth. So all of these are biased estimators. We will not be estimating these. Sort of. See, standard deviation, if we get large enough, then the standard deviation of our sample does approach the standard deviation of the population. But for now, we aren't going to be using these to estimate, okay? The means are unbiased. We just saw that when I did the mean of the means, it equaled the true mean, okay? So the means are unbiased, which means, I'm going to write that down. Right, the mean of our means equaled the true mean. Proportions are unbiased. If I do the mean of proportions, it's equal to the true proportion. Okay? Variances are unbiased, and that's another one we use. We're not going to be using this specifically in this class, but that's another one that if you looked at, variances are unbiased. They will estimate the truth. But these are the two that we're going to be focusing on the most of this class. So like I said, a lot of the homework is just going to be you verifying this. I want you to see that, but when we're using these in the future, means and proportions we can use to estimate the truth. Okay? So let's do an example here. Let's roll a die. We have the numbers 1, 2, 3, 4, 5, 6. What is the mean of those numbers? Well, if I added them up, 6, 12, 16, is it 21? I'm not sure. Let me double check that again. 6, 12, 16, I think it's 21. Divided by, there's 6 numbers, should be 3.5. Okay, so our mean is 3.5. Okay, what if I was to do several sample size 2? So I would basically pull a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6, a 2 and a 1, a 2 and a 2, a 2 and a 3, 2 and a 4, 2 and a 5, 2 and 6, I forgot 1 and 1 there, sorry, a 3 and a 1 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2. See, this would be it. How many would there be in total here? 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So there are 36 different ways we could sample size 2 from these 6 numbers, right? Now, keep in mind, I'm talking about rolling a die. I could roll a 1 and a 1, a 1 and a 2, a 1 and a 3. So there is some duplication allowed here, okay? But this is not a sampling distribution. These are still individuals. If I wanted the sampling distribution, what the sampling distribution would be the collection of means. So the average of 1 and 1 would be 1. The average of 1 and 2, the average of 1 and 3, the average of 1 and 4, all the way to the last one of the average in 6 and 6. So we would have 36 means. That would be the sampling distribution. Okay? Good news is I've taken the time. You can pause this if you want and do this as well. But I've taken the time to type this all in. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. If I scroll all the way down, there are 36 options ending with 6 and 6. Okay? So like I said, if you want to pause and type all those in, you can. But to get the sampling distribution, what we would do is remember, is this a sampling distribution? These are still individuals, right? So it's not a collection of sample statistics. What I would do is I would say, okay, take everything in A bracket. Make sure I do this right. A bracket. A bracket. I'm going to get this eventually. There we go. Plus B bracket. And we're going to take that group. So I actually need to group those. I'll put this parentheses here. It looks like it grouped it. And divide that by 2. So 1 plus 1 divided by 2, 1 plus 2 divided by 2, and hopefully, all right, mine gave it to me as fractions. So if I want these as decimals, I would go to my settings and change this from, where is it, auto to approximate. So now what that's going to do is when I run this, it's going to give me decimals, okay? So that was on the home screen, settings, document settings, change it from calculation from auto to approximate, okay? Approximate, okay, go back, they're all decimals now, okay? Cancel, cancel. All right, so what is the mean of these 36 means, right? What is the mean of all 36 means? Well, I think we can do that. Menu, statistics, distributions, no, calculations, one variable stats. The mean of our means is still what? 3.5. So the mean of our means is equal to 3.5, which is equal to the true mean there. They are equal. The standard deviation of the means, I'm not exactly sure which of these to use, so I'm going to double check this, but settle down there. What was it? 1.22 or 1.21 basically. So they're going to be close anyway, but 1.2247 or 1.207. And 1.2, is it 247? Oh, 207 and 2247. And the other one was 2247. Okay. That is not going to be the same as the standard deviation of the population. If I have the standard deviation of 6 numbers there, that's not going to equal that same standard deviation. Okay. It's actually going to be less. If I just had the numbers, just 1 through 6, Just 1 through 6 on the side here. 1, 2, 3, 4, 5, 6. And I ran one variable statistics just on that. It would tell me my mean of 3.5, but it would tell me a much larger standard deviation. Okay, so 1.87, 1.77, I'm going to put the 1.87 here. And sigma was 1.7078. Okay, and notice that's not the same. There's actually less deviation. We would expect that, right? Because when I'm dealing with the population, we're dealing with individuals, okay? So the standard deviation of all those individuals, you would expect more deviation with individuals than you would with a mean. Individuals deviate more than groups. This represents a mean of groups. So this represents, right? This represents less deviation. For example 3, what I want to do is I want to just deal with this with proportions real quick. So if I said the numbers 1 through 6, and I said, okay, so what is the proportion of 6's in this? Well, the proportion of 6's is 1 out of 6, correct? Well, what if I took each of these samples and I made a collection of proportions? Okay, so I'm going to go back to this and say, go back to the original data here. And what I want to do is I'm actually going to, rather than find a collection of means, I'm going to clear this out and we're going to do a collection of proportions. Okay, so how many 6's are here? Well, none. Here, none. It's not terribly exciting for now. But all of a sudden, what? We have 1 out of 2. This is still a collection of proportions. This is, we're saying how many 6's are there? Well, 2 and 1. There's none there. None here. None here. Till we get all the way to what? Then we have 1 out of 2. How many 6's are here? And then we have 1 out of 2. And then again, and then 1 6 out of 2. And then none, 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 1 out of 2. And finally, here's where things get exciting. How many 6's are there? 1 out of 2. 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 And 2 out of 2. Or just 1. 100%, right? This is a collection of proportions. This is a sampling distribution. So what I have here is we would say out of those 36, okay, then I could say the proportion of those, we would have a collection of proportions would be 0, 0, 0, 0, 0, 1/2, 0, 0, 0, 0, 0, 1/2. This is how many 6's are in those samples, right? 0, 0, 0, 0, 0, 1/2, 0, 0, 0, 0, 0, 1/2, and almost there. And then we got to the 6's and things got exciting, and we said 1/2, 1/2, 1/2, 1/2, 1/2, what? What do you think the mean of these proportions will be? Well, let's see. It should have updated. So if I scroll up, it should have updated the mean right here for our group. Well, If my calculator doesn't get too excited here. Oh, lordy. Come on. Is 1.1666667. Well, 1/6 is, what do we notice? The mean of our proportions is equal to the true proportion. Well, the true, no hat there, the true proportion, okay? So that's why means and proportions are unbiased, okay? I'm going to not do it this way. I did it a little differently this time, so I'm not going to mess with those. So, but basically, the mean of the proportions equal the truth. Therefore, proportions are unbiased. And I want to do one more thing just to kick this up a notch, because really all of these are kind of small scale. What's kind of neat is if I just took the population 1 through 6, okay? So if I just took the numbers, I'll do one more screen here. If I just took the numbers 1 through 6, okay, and I called that our population. Okay, if I was to graph that population would not be normal. In fact, it would be a uniform distribution. Each one would have 1 out of 6, right? Well, what if I did a sampling distribution? Well, we did that, didn't we? Go back to this same list. I kind of messed with it a little bit. Let me do it right here. I'll do, what was it? A plus B divided by 2. And this represented all those means. And I'm going to call this mean, MEAN2. Okay? Because it was mean with a sample size of 2. How is this distribution of sample means going to compare to the population? Well, the population was uniform, right? If I change it to the means, that is no longer uniform, is it? In fact, it's become more what? Not perfectly, but it's actually become more normal. See that? So if I kick this up a notch and I said, what if we did sample size 3? So that would be 111, 112, 113, 114, 115. That would be a total of 216 stinking options, right? Who would take the time to type in all those numbers? Well, I did, but it's kind of my job. Dang it. Just trying to get to 216, showing you it ends on the 666, 665, 666. All 216 options. What I've done is I've increased the sample size, right? So I'm sampling 3 instead of sampling 2. And so if I did the mean of these numbers, right, that would be A plus, oops, I'm going to actually open the parentheses first. A plus, maybe, plus, oh my gosh. Sometimes technology is fun. Plus B I can't even see. There's no B there. Why is there no B? B plus C all divided by, now there are 3 numbers. The average of 1 and 1 and 1, the average of 1 and 1 and 2. This is a collection of means. This is a sampling distribution. I'm going to call this mean 3, because we had sample size 3. What happens as I increase the sample size? Well, here's the population. Sample size 2, it started becoming pretty normal. Kick it up. Sample size 3, it's becoming more and more normal. Okay, and the mean of those means, the mean of the sampling distribution equals the true mean, but the standard deviation is not the same. This leads us, they're really trying to get you to see our last section is going to be on really the central limit theorem and seeing normality. So this, I want you to copy it down now. We're going to have a different set of notes for this, but for any population with a mean and a standard deviation sigma, the mean of the means equals the true mean. We've seen that. That's what we're seeing in this section. Okay? The mean of the means, the mean of the sampling distribution, equals the true population mean. Second, the standard deviation of the means does not equal the true standard deviation. It's sigma divided by square root of n. The standard deviation of the means of the sampling distributions is not the same as the population, but it's the population standard deviation divided by the square root of n. And I want to go back and I want to look at this right now. But this is only true, right, for any population. This is true if we have normality. So this is the central limit for any population with a mean and standard deviation. The mean of the means and the standard deviation of the means will equal these values right here. Okay. This has some requirements on it. You must either have normality or you have to have a sample size greater than 30. Some will say greater than or equal to. I'm going to call 30 fine. So if we get to 30, it's going to be close enough. But some will say greater than 30. I'm not going to split hairs on that. So just greater than or equal to 30 will be fine for me. Okay. But if we get a sample size great enough, then basically the central limit theorem kicks in where the mean of the means will equal the mean. The standard deviation will be sigma over square root of n. And the distribution becomes more normal. Okay, we'll talk about that more in the next section.